So the following are the 6 methods: optical probe methods, electron probe methods, scanning probe methods, spectroscopic methods, ion particle probe methods, thermodynamic methods. Spectroscopic methods are also known as photoprobe characterization methods. Most of these methods involve a primary photon in and a secondary photon out. UV visible spectroscopy is the most common method. The two relevant X-ray techniques are XRD, that is X-ray diffraction, EDX, that is energy dispersive X-ray. So there are various spectroscopic methods, and they have various outcome from each and every spectroscopic method. So basically we will be dealing with spectroscopic technique. So spectroscopic methods are of various types, and each method has its own importance. UV visible spectroscopy is basically a chemical analysis technique. The details of this technique will be explained by one of my college colleagues. Apart from that, there are several other spectroscopic methods. As you can see here, that is a surface plasmon resonance spectroscopy (SPR), Raman spectroscopy (RS), surface enhanced Raman spectroscopy, that is SERS, Fourier transform infrared spectroscopy, that is FTIR, XRD, that is X-ray diffraction, energy dispersed X-ray, that is EDX, X-ray fluorescent, that is XRP. However, my focus will be on Fourier transform infrared spectroscopy. So what is this IR spectroscopy? IR radiation is largely thermal energy. It generated stronger molecular vibrations in covalent bonds. Thus, vibrations which are associated with the change in dipole moment of the molecules, such as organic or inorganic, are called infrared active transitions. Otherwise, the vibration is said to be the infrared inactive, and that do not show any absorption band in IR spectrum. The most frequent spectroscopic is this IR spectroscopic technique, which is being used by various chemists in different countries. So it deals with the absorption of radiation in the infrared region of the electromagnetic spectrum, that is between 4000 to 1300 centimeter inverse, and then 1300 to 400 centimeter inverse. Bands that are unique to each molecule, like a fingerprint, and are found in the fingerprint region, are between 400 to 1300 centimeter inverse. IR spectrum gives sufficient information about the structure, that is identification of the functional group of a compound, and can also be used as analytical tool to assess the purity of a compound. These bands are only used to compare the spectra of one compound to another. So infrared radiation is largely thermal energy. It induces stronger molecular vibrations in covalent bond, which can be viewed as springs holding together two masses or two items. Specific bond respond to absorb specific frequencies. As you can see, there are vibrations which can be divided into stretching and compression. Stretching means the two bonds will be stretched, and compression means they come closer to each other. So stretching is further divided into symmetric and antisymmetric. When distance of bonds remain same, so you can see here the symmetric and unsymmetric, and they are further divided into bending, or more precisely scissoring. Generally, larger the change in the dipole moment, the greater is the intensity of absorption. Hence, the vibrational absorption bands in simple hydrocarbons are very weak, while bands associated with bonds connecting atoms, most like electronegative items with high electronegativity difference, give strong bonds. So these are the two types of the bond vibration. You can see in this slide the vibrations or the oscillations along the line of the bond. So you can see along the line of the bond, this is a stretching, and this is equally stretched. That's why it is known as symmetrical stretching. And you can see this is asymmetrical stretching, so it is unequal bending. So vibration or oscillation not along the line of the bond. So you can see the angle of this is changing. So it is inside the plane, so in plane. This is outside the plane, so out of plane. So let's have the information of about the IR spectrometer. So this is a basic structure of the IR spectrometer. When a chemical sample is exposed to the action of the IR light, that is a source, it can be absorb some frequencies and transmit the rest. Some of the light can also be reflected back to the source. The beam from the source is divided into two equivalent beams, one passing to the sample and the other to the reference beam. Alkali metal halides such as potassium chloride, sodium chloride are commonly used as they are transparent to the IR region. The sample absorbs strongly in most of the IR region. The monochromator is a device used to disperse or separate a broad spectrum of IR radiation into a continuous spectrum of frequencies of IR light. Detectors, they are the devices that convert the radiant energy into an electrical signal. The detector determines the ratio between the intensities of the reference and the sample beams. Due to the difference in the intensities of two beams falling on the detector, an alternating current starts flowing from the detector to an amplifier, where it is amplified and relayed to the recorder. So this is our recorder. Recorder records IR spectrum as a plot. You can see as a plot of frequency of absorbed radiation and intensity of absorption, that is in terms of transmitter. Unlike UV spectroscopy, here we use the wave number unit. As the detector records the intensity of the two beams, therefore percent transmittance is recorded. From all the frequencies it receives, the chemical sample can absorb specific frequency and allow the rest to pass through its, that is, transmitted light. Now let's have the more information of the advanced version, that is a nano FTIR, that is nanoscale Fourier transform infrared spectroscopy. So basically the nano FTIR is based on a SNOM that is scattering type scanning near field optical microscopy. So this setup comprising an asymmetric interferometer. So asymmetric interferometer where the AFM, that is atomic force microscopic tip, and sample are located in one of the interferometer arms. A broadband source, for example laser, synchrotron, etc., they eliminate the AFM tip and the tip scattered light. So you can see the scattered light, and this light is recombined with a reference beam at the detector. The detector, that is what we have seen in the FTIR, normal FTIR. The detector signal is recorded as a function of reference mirror position, creating an interferogram which is processed by FTIR based detection. So moreover, this normal FTIR and the nano FTIR have the same type of assembly